So I wanted to come back to this slide. I was re-reviewing, or I should say, I was reviewing my video, and I wanted to explain this a little bit better because I did a pretty crap job explaining this. So I'm gonna erase this, and I want to go back and really get into the details of this background single beam versus sample single beam, okay? Because I did not do a good job explaining that. And also I realized that I've got a bit of a mistake on my slides. So I'm going to label everything really carefully. We've got I0 and I, and I'll say that this is I0B for the background and IB for the background. And then we've got I0S for the sample and IS for the sample, okay? And so if we were to, so I've drawn a detector, the detector would be in the same position, right? Because it's the same instrument. And so if we were to look at what the single beam spectrum actually looks like, I wanted to go into that, okay? We can actually get a spectrum from each single beam, and it's going to be given as intensity versus wavelength, okay? Because each single beam spectrum is not going to be an absorbance spectrum. It's really going to be, if you think about it, it's an emission spectrum from the lamp itself, right? So I'll draw our little lamp right here, okay? So this is radiating out. Right, and particularly for the background single beam, since we're only going to get these scattering events, generally what we will see is a nice looking Boltzmann distribution, okay? So it's going to look something like this, because that's what the intensity of our light source would look like, all right? And so now over here, we've got the same light source, but now we've got some absorbing samples, okay? So this sample single beam spectra is still going to have this Boltzmann distribution of wavelengths, of intensities. However, if there are absorbing molecules in there, they're going to remove some of that intensity. So our sample single beam would actually look something like this with these features removed, okay? And so we still have this Boltzmann distribution, right? But there will be some specific frequencies that have been absorbed out of this intensity, all right? And so now if we think about this log ratio of ratios, then what will remain is the intensity of the background over the intensity of the sample, okay? Because everything, I0 background all the way up to this point will really be identical to the sample, with the exception, of course, of the intensities that have been absorbed, all right? So really now what this means is this absorbance is going to be the negative log of I sample, so the transmitted beam coming out of the sample over the transmitted beam coming out of the background, okay? So both of these two things will wash out because they're identical. And so now what our absorbance spectrum will look like, okay? So we'll have absorbance versus wavelength, right? And I already showed you in the other slides, let's see, right up here, right, where we take the log ratio of two identical single beam spectra, it's just going to be 0, and we'll have a flat line about the 0, right? So what that means is where our intensities are identical, so I'll put a 0 point here, we would see a 0 line, okay? And now where we see these features that have been removed, okay, because that's the, the intensity of the single beam over the background, and it's the negative log, these negative intensity features will appear as positive peaks. Okay? So that is a much better description than what I did previously. So I just wanted to take some time to walk you through that. Okay? So let's get into pure rotational spectroscopy. All right? So the key molecular property in rotational spectroscopy is the moment of inertia given by mr squared. Okay? And so if a molecule doesn't have any moment of inertia, then it doesn't have a rotational spectrum. Okay? And so you also notice here that I've given this as a sum, and that's because for a very, very simple object, such as two masses on a spring, there will only be one moment of inertia. However, for more complicated looking molecules, there will be multiple moments of inertia. So we'll have a sum there. And I just want to kind of describe this briefly. We have linear rotors. And so HCl is our classic example of a linear rotor. Okay, so examples are HCl, something like CO2, right? So linear molecules. So it doesn't just have to be a diatom. It could be something like carbon dioxide as long as it's linear. And the important thing to note with linear rotors is you get, if you think about the moments of inertia that this thing can have, okay, so if it spins like this, round and round and round about that bond axis, there's no moment of inertia there, right? It's just spinning round and round and round. It doesn't look like anything has happened, okay? However, if it spins this way, there is a moment of inertia there, particularly if one of these masses, well, definitely if one of these masses is bigger than the other, right? As that mass swings around, that's going to create a moment of inertia, okay? And so, of course, if we swung it around the other way, right, we would also get another moment of inertia there. So we say that there's two equal moments, okay, given by mr squared. Now, in the case of getting into more complicated molecules, we're not going to get a straightforward mr squared. It's going to be a little bit more complicated. We're going to have to consider these angles, so there's going to be a cosine dependence there. And I don't want to get into those details. But what I want to point out with these symmetric rotors, the way we can start thinking about how many moments of inertia there are is if I look at an XYZ coordinate, all right, Z, X, Y, and I really start thinking about how I can rotate this molecule based on this coordinate system. Well, you notice here, if I rotate it just around this Z-axis, that's going to create a moment of inertia because of these masses that are swinging around. And we call that the I parallel. And then also, if I rotate around these axes, okay, both of those are going to be equal. So now you have to imagine the green atom there, tumbling over this way or tumbling over this way, right, between X and Y. So those two are equal. And so we call those I perpendicular. Okay? So we have two equal moments and one different moment. And so good examples of these symmetric rotors would be like NH3. And NH3, because it has that lone pair on top, right? CH3Cl, right? You could probably have come up with that based on this picture. So I realized I got my two pictures backwards here. So the water molecule is an asymmetric rotor. This methane molecule is a spherical rotor. So I mixed these two things up. And the important thing to note with spherical rotors, there are three equal moments of inertia, right? So if I rotated about that axis, if I rotated about that axis, or if I rotated about that axis, those would all be the same. And so as you might imagine, something like, methane, or even we could add something with non-tetrahedral geometry, SF6, it would be another great example of a spherical rotor, right? Something that's symmetrical all the way around. Okay, so I know a symmetric rotor, you might think, well, why not SF6? And so the important thing with the symmetric rotor is it's got one symmetrical axis. The spherical rotors have 3 symmetrical axes, okay? And then so finally, the asymmetric rotors, such as water, as you might guess, all 3 of those moments of inertia are not equal, okay? So I'm not going to spend a whole lot of time getting into all of these specific examples and coming up with these equations. It's important to note, though, that when we think about the rotational spectrum, and I'll note that that is the microwave spectrum, right? Hopefully we remember from our review of StetMech that rotations occur under microwave frequencies. So we can use a microwave frequency to stimulate a rotation. And that's exactly what your microwave does to heat up food. It actually causes H2O to rotate. And in a condensed medium, so molecules don't like to rotate when they're liquids or solids, so it builds up a lot of excess heat. Okay, so moving on. So hopefully we recall this from chapter 8, right? A nice classic review. I'm just gonna kind of just remind you of the few things that we came up with for our, our particle on a ring model. So we use this to describe an electron rotating around a proton, and that model worked really well. We could also use this exact same model to describe a, molecule with one mass on a spring and a molecule with another mass rotating about each other. Okay, so we could apply that to the electron-proton system, or we could apply this to our rotors, our actual molecules. Okay, so recall the classical kinetic energy is given by p squared 2m. The angular momentum, classical, is given by plus minus momentum cross r, right? And we remember that when it's with our right-hand rule, when it's pointing in the right, when it's rotating, I've blanked out here. When my thumb is pointing up, it's rotating this way. And so the angular momentum goes up when it's rotating in this orientation, and the angular momentum points down when it's rotating in the opposite orientation. Okay, so I equals mr squared for simple rotors. So that would be a linear rotor and nothing else. All of the other rotors have much more complicated moments of inertia. Okay, and so what's important to note when we solved Schrodinger, okay, right? H psi equals E psi. This is the solution that we got for energy. L times L plus 1 times h bar squared over 2 times I. Okay? Well, that's for a single electron. That's the single electron solution. When we apply this to our actual rotors, like HCl, for example, that's a multi-electron situation. Okay? And so for a multi-electron, recall we have to use quantum number J, which is capital L plus capital S. And we remember that capital L is, the Clebsch-Gordon series for all of the small l values. Okay? So what's important is what we can show when we apply this to multi-electron systems, all right, then simply this solution can just become E equals big J times J plus 1 times h bar squared over 2I where J can take on values 0, 1, 2, etc. Okay? And this J right here is going to represent our rotational quantum number. Okay? And so again, if we were dealing with complicated rotors, where we have to take the sum of all of these individual moments, our energy solution would also have a sum. We would have to sum our J values over all of those varying moments of inertia. We're just going to stick with the simple examples so that we don't have to carry out that sum, and also because it's an easier demonstration. Okay, so let's move on. Okay, so we note that E sub j equals j times j plus 1 h bar squared over moments of inertia. Okay, so as it turns out, these collection of constants h bar squared over 2I is what we call the rotational constant, and this is given in joules, right? So if I use kilograms and meters squared and joules for h bar, I'll have B in joules. Okay. So now we're going to come back to this nomenclature that I introduced at the very beginning of the semester. When we put a little tilde on there, that's the rotational constant in wave number. And we can get to the, so we can always convert an energy into a wave number by multiplying by hc. So if I say hc times b equals h bar squared over 2I and rearrange this equation, this is where this comes from. Okay, so as you can see, I divide the hc over, and so that's going to be h bar squared over 2hc over I. And now it becomes convenient to try and absorb some of these constants, right? To absorb the h's together. So I'll leave one h bar here and one h bar here. Excuse me, I'm going to make that just an h, rather. Because we know that h bar is equal to h divided by 2 pi. Okay. Well, then there's another 2 and another hc over I. So that means this h and this h cancel. And then that's where I get the 4 pi ci under h bar. Okay. And of course, I would have to have my, all of this would actually come out in inverse meters, right? And so then I would have to either use all of my distance units as centimeters, or I calculate it in inverse meters and then multiply by that factor, 100 centimeters in 1 meter. Okay. So now if we look at the rotational energy levels in joules, right, that will be given by J times J plus 1 times B. And we'll use the letter F to denote the rotational energy levels in wave numbers. And that will be also J times J plus 1 times the B tilde, right, the rotational constant in wave numbers. And let's see here. Yes, and so, of course, right, to get an actual energy level diagram, what we recognize in spectroscopy is going to be the difference in energy levels, okay? And so that difference in energy levels will be given by EJ final minus EJ initial, all right? And so let me see what I have coming up next. Yes, okay, so let's keep walking through this, okay? And so I just want to show you an example of this. So if I say J equals 0, that's going to be my ground state. And I know that that's going to have an energy of 0 if I apply that J0 through this term, right? Okay, so now what about the next level? Well, that's going to be a J equals 1. And if I make J equal to 1, 1 plus 1 is 2 times 1 is 2. So that's 2 times B. And so the difference right between these energy levels will be 2 times B. So now what about the J equals 2 level? Okay, well, the J equals 2 level is 2 plus 1 is 3 times 2 is 6. So that's 6B. And the difference between these two energy levels is now 4B. Let's keep going with this thing. J equals 3. This is probably as high as I can go on my picture here. So if J is equal to 3, 3 plus 1 is 4, times 3 is 12. Okay, 12b. And the difference between these levels is now 6b. Okay, so this is where this gets a little confusing, because you might expect now your rotational level diagram to have increasing energy spacings. But what we have to remember is there's a population of states of rotational levels, right? So if I look at the J, the nomenclature of this goes J10, so we're talking about transitions from 0 to 1, okay? So we get that to be 2b. Well, what about the J21 state? All right, well, we know that that's going to be 4b. The difference between these two is 2b. Okay, so let's look at the next one, J3 to 2. And so we know that one is 6b. But look, the difference between these two is 2b. All right, and if we were to keep going up, we would see this constant 2b difference, 2 times b, between each level. So each level is growing by 2 times b. And because our molecules will have a population of rotational states, in other words, before we even excite this molecule with microwave energy, it's already going to have populations in level 3, level 2, level 1, level 0. And so what that means is we're going to see a spectrum with spacings every 2 times b. Okay, and I'll show you that here in a moment. So if we think about the selection rules, a molecule must contain a permanent electric dipole moment to give rise to a pure rotational spectrum, because that is going to give it a moment of inertia, right? And also, if we think about the selection rules with our photons, we know a photon has S equal to 1, which is root 2 h bar angular momentum, okay? So if suppose this is the J equals 1 level, and this is the J equals 2 level, we know going from a difference of 1 to 2 is also going to give me root 2 h bar, right? It's going to be J times J plus 1 root h bar for the angular momentum, okay? So that means this molecule going from J1 to J2 will have absorbed root 2 h bar angular momentum. If the molecule relaxes from an excited state to a ground state, it will lose root 2 h bar momentum, which is exactly the angular momentum of a photon. And so that means that it can emit a microwave photon going from 2 to 1, or it can absorb a microwave photon going 2 to 1. And because that root 2 angular momentum is conserved, all delta J values have to be plus minus 1. Okay? I'm not going to discuss these with too much detail, but we note here the delta K being equal to 0. That means we are staying within the same electronic level. So if we were in our ground electronic state, the microwave energy is not going to pump it up to another electronic ground state. And that just kind of makes good sense because of the energy requirement to do that. Okay? And then also our delta Mj has got to be 0 or plus minus 1. And this is also due to our angular momentum that must be conserved. Okay? So moving on. So here is a good example. So this is carbon monoxide. And now specifically, you notice that this is carbon 12O16 because the isotopes in rotational as well as vibrational spectroscopy are really important, right? Because if the rotational spectroscopy is all about the moment of inertia, then the masses of those isotopes are critically important. So a rotational spectra as well as a vibrational spectra is a good diagnostic tool to probe isotopes and the isotope effect, which is really cool. Okay, so now let's chew the spectrum apart. So here I was showing you how I put that together before, how each of these levels grow by 2B at a time, right? 2B, 4B, 6B, 8B, 10B, 12B, etc. So then now the difference between each one of those is 2 times B, okay? So delta EJ equals 2 times J prime times B, where J prime is the upper level. So for example, when J is equal to 0, this whole thing is equal to 0. But when J is equal to 1, 2 times 1, right, gives me that value, okay? All right, very good. So here we can see this nice, lovely rotational level spectrum. And you notice here that it has this lovely Boltzmann distribution, okay? And it has a Boltzmann distribution because each of those states at 40 Kelvin are populated. So we're going to see a 0 to 1 transition. We're going to see a 1 to 2 transition, a 2 to 3, a 3 to 4, and so on and so forth. And you notice for this sample, after about, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 9 to 10 is showing us that that's the least intense transition. And so that's because at 40 Kelvin, the carbon monoxide is not going to have a population above that line. Okay? And so what I also want to point out now is if we start looking at the actual frequencies, so we can look at this in terms of wavelength or frequency, right? So here this is given as frequency in megahertz, and that's microwave radiation. Okay, so these are microwaves. And now you notice that they are going up by this even amount. And if you look at the spacing, it's approximately 115,000 megahertz. So if it's supposed to be one of these spacings every 2 times B, right? Let's note that, 2 times B. Then why are they not exactly 2 times B each time, right? What is going on there, okay? Well, as it turns out, when this sample rotates, it experiences what we call centripetal distortion. So those bonds are, in fact, not rigid, okay? And so as this molecule is being spun around, those bonds are being elongated. That has the effect of changing its moment of inertia and, of course, also its angular momentum. And that effect becomes even more pronounced at higher J levels, okay? So these first few levels, especially like this very first one from 1 to 2, at 115, 266, or even the 0 to 1, 115, 271, those are likely the true value of B, okay? So I'll point to this ground state 1. Because, again, at that small rotational level, at the ground state rotational level, there's not a whole lot of centripetal distortion going on, all right? And so as it turns out, that centripetal distortion effect can be given by the J constants as well as the distortion constant, okay? So that's given by D, all right? So that's the distortion constant. And so you notice the effect of this is that it reduces the energy level, because as the bond is being elongated, you have to kind of think of what I like to call the quantized ice skater, right? So imagine an ice skater spinning round and round and round. As you bring your hands in, you rotate faster, and as you bring your hands out, you rotate slower, okay? So as it's being distorted, as those bonds are being distorted out, it's gonna slow down its rotation. And the effect of that is it reduces the apparent energy spacing. It doesn't change the rotational constant, but you can see because there's a subtraction there, it's going to reduce the spacing between energy levels. And as we go down this series, you can see each time those levels are decreasing by, it's a fairly constant amount. It seems like it's a constant amount, but it is based on this J squared, okay? And so the other thing I'll point out, the distortion constant is also dependent on the vibrational energy, okay? So we're going to talk about that soon as well, but that's what that constant gives us, okay? So I got to see what I have next. Okay, so the next thing that I want to do, so I've been talking about 30 minutes, so I'm going to cut it off now. But what I want to get into next, still getting into this rotational spectra, I want to really get into this in nice detail because this is cool. The rotational lines are actually a molecular thermometer. So we can actually use a rotational spectrum as a thermometer, which is really cool. And I will describe that in more detail in the next video.